Hello, and welcome back to Forensic Bites. Today we're starting a new series called Evidence Collection in Forensic Science, and our first topic is what's in a fingerprint. What we're going to be covering is we're going to be looking at the chemical composition of fingerprint residues. Now, that's not necessarily simple in that there is a timing element to what the composition of a fingerprint is actually going to be. So we're going to be discussing a little bit how the chemical composition of fingerprints changes with time. We're also going to talk about some of the implications of changing composition of fingerprints and how that impacts certain types of evidence collection, primarily fingerprint visualization. Lastly, we're going to discuss the limits of fingerprint persistence on different types of surfaces encountered by forensic practitioners. To start out, fingerprint residues are an emulsion that's comprised of the output of two different types of glands. First of these is the eccrine gland, which you probably would think of as your sweat glands. Sweat glands release aqueous components, so primarily water, amino acids, various salts, and other types of highly polar chemical molecules. The other type of gland is the sebaceous gland, and this is one that releases oily, non-polar residue. The combination of these things is called sebum, and it contains squalene, fatty acids, esters, and other similar non-polar chemical species. The eccrine output, or sweat, is largely used for temperature regulation, whereas sebum is more for skin and hair health, as well as some degree of protection from things like UV radiation. Looking more at the non-natural material that you might have on your fingerprints, exogenous material from handling objects, applying things like makeup, or anything that you might handle that's transferred onto the surface of your fingers may be present when you touch a surface in your fingerprint. To focus initially on the eccrine components, so sweat contains amino acids that can themselves be targeted by certain chemical visualization treatments for fingerprints. Now, the primary chemical treatments that we use to visualize fingerprints are ninhydrin and indane-dione. These are used on porous surfaces and they target the amino acids that are transferred into those surfaces. The top two amino acids secreted in sweat are usually serine and glycine, and we can see that in the graph on the right. One of the traits inherent to these amino acids is they typically contain polar functional groups. And that makes a lot of sense given that sweat is an aqueous medium, so the amino acids that are more soluble in water are more prevalent, whereas the hydrophobic amino acids typically aren't found in high concentrations in the eccrine secretions. In the graph, we can see that alanine is probably an outlier. However, if we look at the structure of alanine, it has a relatively small non-polar side chain. So we could nearly class that as being similar to glycine in that respect. Now, sweat also contains ionic components, primarily sodium, potassium, calcium, and chloride. All of these are naturally produced by the human body. There are other metals that can either derive from the body or may have an external source, such as cosmetics, and these can also be detected. And examples of these include iron, copper, and zinc. There may be other metals that arise purely from an outside source, such as titanium, bismuth, nickel. So if we have a look at the diagram, we can see some of these metal species that were imaged using X-ray fluorescence microscopy. So these experiments were done with a synchrotron, which is an extremely powerful source. So this is probably not typical of an experiment done in a forensic laboratory, but it's interesting that they are potentially transferred onto surfaces with touch, as these could pose a future analytical target for detection by forensic personnel. Shifting over to sebaceous compounds, these represent an incredibly wide variety of chemical species, many of which have been catalogued without quantitation. So while we may know that they are there, we don't necessarily know how much of this material is typically transferred. Not featured in the list is squalene and cholesterol, even though these are found in sebum in quite high levels. Now, this mixture can be targeted for other visualization treatments. So initially we talked about ninhydrin and indane-dione for targeting the amino acids in eccrine secretions. Here we'd target the sebaceous residue with different techniques such as iodine fuming or oil red O, ones that really target the non-polar residues. Now we need to understand a little bit about the surfaces and the time component when we're looking at fingerprints. So the surface on which a fingerprint is deposited and the time which it has sat there each can impact a fingerprint's composition. This is important since some development techniques will only function within a certain range of time that the fingerprint has been deposited. So if we have a look at the diagram, we can see at the very top, time equals 0, like the point at which you have laid a fingerprint onto a porous surface. And a typical porous surface is something like paper. So when you touch it, it is going to sponge in the chemical species into itself. So at time equals 0, we have the residue basically sitting on top of the paper. But in the order of seconds to minutes, what we get is the water-soluble component of the emulsion being drawn down into the paper. And when that happens, it takes the amino acids with it and potentially also the salts as well, and things like urea. Now, this is important because those components can be targeted in fingerprint visualization, and they're also somewhat protected when they are drawn down into the paper. So if you were to brush the surface after the fingerprint has been put there, you might be able to wipe away the water and soluble component sitting on the top, whereas the water-soluble component has been drawn down inside and will remain there afterwards. Now, assuming that hasn't happened though, the sebum, or the water-insoluble component, will remain exposed on the surface for days to weeks. But protected inside, the amino acids can sit for extremely long periods of time, in the order of years. And if you want to develop those chemical species that have been drawn into the paper, the best way to do it is to use a chemical development method. So you spray your chemicals onto the paper, they too are drawn inside, and they can interact with the amino acid to form either a visible or a fluorescent dye. Looking this time at non-porous surfaces, in this case, the entire emulsion will remain exposed on the surface because it being a non-porous surface like glass or stone, there's no way to absorb material inside of itself. So what happens is the volatile components will evaporate. So the water, anything that's low molecular weight and has volatility, is going to dissipate and evaporate and disappear in the order of weeks to months. What's left is a dense residue that contains elements of both the eccrine and the sebaceous glands. So you've still got the amino acids, you've got urea, you've got salts, you've still got the long-chain fatty acids because they're not particularly volatile. All of these are remaining exposed on the surface. But because of that, they're potentially subject to physical damage or erasure if the surface is cleaned or rubbed. Now, having the bulk of the residue present, ideally on a flat surface, makes it very exposed to things like fingerprint powders. So if you're dealing with a non-porous surface, one of the best ways to visualize the fingerprint is to dust using fingerprint powders. And the dust will stick to the residues that are there, and it will create contrast in that way. So to conclude, you really need to know about fingerprint composition, how old the fingerprint is, as well as the surface type that it's on, for you to make an optimal selection of what development technique that you're going to use. Porous surfaces will bring water-soluble components into themselves, and because of that, they're going to benefit from chemical techniques that can also absorb into the paper and target those components. Non-porous surfaces lend themselves more to a powdering technique, so that the powder can interact with the residue that is still present on the surfaces. Most techniques will benefit from fresher fingerprints, although not all. So for example, Physical Developer is one technique where it's known that it requires a few days of fingerprint aging to get the best results from the surface. That concludes our quick summary of what's present in fingerprints. Thanks for listening.